and let's switch back to the University of Melbourne and Michael Wheeler, expansion coefficients in the Yang-Baxter equation. Thanks, Michael.
Yeah, thanks very much. I'd like to begin by thanking the organizers, Murray and Vladimir, for the opportunity to speak here. I will say that I did not know Rodney personally, but clearly his work has been absolutely inspirational to me throughout my whole career. Indeed, it's very hard for me to find a paper where I do not use a lattice model or the Yang-Baxter equation in some form. And the work that I'm going to talk about today is no exception to that. So this is a joint work with Ajith Gunnar, also from University of Melbourne. And I'll begin with a few words of basic motivation, mainly to say the problem that we're interested in. So there's been a program of studying symmetric functions via integrable lattice models that I've been part of for the last 10 or 15 years. And really, by now, there's pretty well worked out dictionary between things that appear in integrable models and concepts that arise in the study of symmetric functions. So when you take your favorite symmetric function and express it as a partition function of a vertex model, a number of properties can arise, which are indicated in this table here. So the first thing is that these are supposed to be symmetric functions in a set of variables. And at the level of the lattice model, this is nothing but the property of commuting transfer matrices. Another property that you typically have in symmetric function theory is you have what are called symmetrization identities for the family of polynomials that you're looking at. And in terms of lattice models, this is nothing but the coordinate beta ansatz type expressions that arise. And at a slightly more sophisticated level, one of the things that people also care about are these Cauchy summation identities in the theory of symmetric functions. And one way to prove those is essentially to use either the Yang-Baxter algebra, or as it's sometimes referred, the RTT relation. So this is a picture that is now very well developed for many years. And what we would like to do is push this program even further and study another problem, which is to take two different bases for the ring of symmetric functions and expand one of them, say this family F, in terms of another family G. And when you do that, you get a family of coefficients. And so these are the so-called expansion coefficients, and they will be the topic of this talk. So in particular, we're going to look at the case where you take a Macdonald polynomial and expand over the Shor basis. So I'll begin by saying a few words to define what Macdonald polynomials are. I would imagine that they're well known to many members of the audience. So Macdonald polynomials, they depend on an alphabet of variables, usually denoted x1, x2. And this alphabet can either have finite or infinite length. And they also contain two further parameters that are always denoted as q and t. So these are going to be symmetric functions with respect to this alphabet of x variables. And one way to define them, which is the way that Macdonald actually does it in his book, is to set up two properties and then say that the Macdonald polynomials are the unique solution of those properties. So these are the following. So the first is that you take the Macdonald polynomial and you expand it over a rather elementary basis, which is the so-called monomial symmetric function basis. For anyone who doesn't know what those are, I've included the definition in red here. So essentially, this says that the Macdonald polynomial expands in a triangular fashion over that basis, with the leading term being equal to, or the leading coefficient being equal to 1. So then you have a family of other coefficients here, which you actually don't know very much about them. They're just some rational functions in Q and T, which could potentially be very complicated. The second property is that if you take the Macdonald polynomials and feed them into a certain scalar product, they're actually orthogonal with respect to the scalar product. So the scalar product is normally defined with respect to what are called the power sum symmetric functions. And again, if you've not seen these before, the definition is in red here. So the power sums are orthogonal with respect to that scalar product. And likewise, so are these Macdonald polynomials. So those are the two properties, and it's not at all clear that this actually defines uniquely a family of symmetric functions, but it turns out that it does. Okay, so Macdonald polynomials, they're very well studied, very famous, and they have many nice reductions. So probably the nicest one is that if you take one of those two parameters, say the q parameter, and set it equal to t, then you actually get a reduction to another very famous basis, which are called the Schur polynomials. So a priori, making that substitution, you should still have one parameter left over. It turns out that it actually evaporates completely, and by a miracle, you end up getting an expression that is q independent, and this thing is precisely the Schur polynomial. So Schur polynomials, there are many nice formulas for those. I've given one particular determinant formula, which again is very well known. So in this work, we considered basically a particular normalization of the Macdonald polynomials. This is really a technical detail, doesn't affect too much the underlying mathematics, but we would like to normalize the Macdonald polynomials by some scalar factor here, which is a fully explicit function of q and t, right? So it's basically given by the formula here. So this is a combinatorial expression. It's a polynomial in q and t, and you get this thing essentially by taking your Young diagram and looking at a given box in the Young diagram and working out its arm and leg lengths, which are indicated here, and those become then the exponents of this q and t parameter, corresponding to that particular factor. And then you take the product over all squares in the Young diagram, and that's the definition of this thing. So the reason for making this change of normalization, this was also done by Macdonald, and these things are known as the integral Macdonald polynomials. And the point of interest here is once you have done this normalization, you actually clear all of the denominators that you have in those rational coefficients. So if I go back a few slides, there were these coefficients here in the monomial basis, which are rational functions. And the point of multiplying by this overall factor of q and t is to clear all of those denominators. So Macdonald actually conjectured that these integral Macdonald polynomials are actually going to have coefficients that are now polynomial in q and t, in general with integer coefficients. And this was subsequently proved in two papers that came very close together by Sahi and Knopp. So actually, even though this is fairly nondescript statement here, I'm not getting too much information about those coefficients. It turns out that they were studied quite a bit afterwards, and people managed to get very explicit formulas for these things, which is what's shown on this slide here. So there is some technical detail here that's perhaps not too important for the purposes of the talk, but I want to define a family of polynomials in Q and T, which will take this form generically. So there'll be, depending on an integer I and j, which will be the exponents of this Q and T factor here, and also there'll be a general product here over such factors, where all of the exponents are non-negative integers. So with the definition of such a set of polynomials, there is a very nice combinatorial formula that was obtained in 2006 by Hagelin, Heyman, and Lohr, and they essentially wrote the integral Macdonald polynomial fully explicitly as an expansion over a family of tableaux. Now, these tableaux are not sort of the typical tableau that you have. So these are not semi-standard Young tableau. They're slightly more complicated objects, but nevertheless, they're still relatively simple. And you sum over all such tableau of a given shape with an explicit function here that you prescribe to the tableau, and this then defines for you a fully explicit combinatorial formula. And in particular, what is nice about this is that these coefficients, they're fully factorized. So they're all going to be polynomials in Q and T that have this very nice explicit form at the top of the slide. So in our work with Ajit, we considered an analog of this problem, which is to expand these integral Macdonald polynomials not over the monomial basis, but actually over the basis of short polynomials. And what we would like to do is study these coefficients. And to the best of our knowledge, based on looking through the literature, no one has actually come up with a solution to this problem, and it seems to be relatively unstudied, which is surprising given that both of these are very celebrated bases for the ring of symmetric functions. So we would like to say something about these coefficients, and it turns out that we obtained a fully explicit formula for them, which is a combinatorial formula in the same spirit as the one that I just showed on the previous slide. So one motivation for looking at these coefficients is they're actually the subject of a relatively famous conjecture, also by Hagelin from 2010, which says that if I fix two partitions, so I look at a particular coefficient in this family, and I set the t parameter that appears in the Macdonald polynomial, I will set it equal to a power of q. And it can be any power of q, so I can choose any natural number here. So what Hagelin conjectured is if you take that object and divide by an explicit factor of 1 minus q, this is actually a polynomial in q with positive coefficients. So it's actually a positive polynomial. And in the algebraic combinatorics community, these kind of positivity statements are very topical, and people work very hard to try to prove such statements. For this particular conjecture, there is relatively no progress over 15 years, in fact. And as far as I know, one of the few papers where some sort of partial progress for very special partitions is in this work from 22. So that's one motivation for why you may look at these coefficients. All right, so I will now move on to the statement of the result. And I'm going to suppress a lot of the details in the statement, just give you the bare essence of what we have done. So this is our theorem from the upcoming paper that we will release. So it says that these coefficients, we have an explicit formula for them in terms of a partition function of a certain vertex model. And this vertex model, as far as we know, the weights that we are using are completely new. So this is actually a new solution of the Yang-Baxter equation. And how does the formula work? So first, you have to prescribe some boundary conditions for your partition function. So I'll refer to this as fixing the frame of the partition function. So it will depend on the two partitions in some explicit way. And then once you have done that, you really compute this thing as an honest stat-mech partition function, work out the sum of all possible configurations, and work out then the weight of a given configuration, add all of those up, and this gives you then a formula for this coefficient. And just as in the case that we looked at a few slides back, just as in this formula here, these coefficients are fully factorized polynomials in Q and T. It is also the case in our formula. So the coefficients that we have are fully factorized polynomials in Q and T. There is one thing, however, which is rather unfortunate, which is that even though we get an explicit formula, it doesn't actually enable us to prove Hagelin's conjecture. So Hagelin's conjecture is still open, and what we end up getting is a sum, basically, with some signs in it. And so the terms in the summand here, modulo this sign, what is left over here is actually a positive polynomial. So it's really some sort of alternating sum of positive polynomials, and we're actually unable to show that the whole thing itself is a positive polynomial. So this was rather unfortunate, but nevertheless, that's what we found. So now I will actually show you explicitly on some examples the nature of the formula that we found. So this is the first example where you fix two partitions that have, in this case, weight 2. So it's a relatively small example. And in that case, you get just two terms in the partition function. And so each one of these has an explicit weight. You add them up. And in this case, you'll get the coefficient that you're trying to compute. Let me say a few words about how you actually read off the partitions from the pictures here. So this is probably not clear. So the first thing is that this partition, the partition nu, is obtained by looking at, in this case, the red particle. So this red particle, you can think of it as entering at the base of this column, and then it propagates through the lattice and wraps around the lattice, and then re-emerges and finally exits at the top of this column. And so the column where it exits, in this case, this is column number 2. So this is column 0, column 1, column 2. And so that's the reason why it corresponds with a part of size 2. Now, the other partition, which in this case is 1, 1, is obtained by looking at the blue parts here. So these are heading in some other direction through the lattice, but again, you look at where they exit, and the exiting points determines for you the second partition. So I didn't want to give the precise prescription of the boundary conditions, just some examples that would illustrate the flavor of the result. So I have a few other examples. This is a slightly more complicated one. So here the partitions have weight 4. And well, in this case, you get 5 terms in the partition function. And by adding up the weights of all of these, you get the polynomial that you're trying to compute. Couple more examples. The pictures tend to be quite nice to look at, I find. So this is an example, again, of weight 4. And this one is a little more complicated because the partition nu here actually has 2 parts instead of 1. And what that corresponds to is 2 colored paths that enter through the first, or rather the 0th column here, and exit through, in this case, the 1st column and the 3rd column. So this is what you obtain. And one final example, this one with 6 terms. So one thing that I want to stress about this is that the number of terms that you obtain here is actually a tiny fraction of the number that you would obtain if you just did a brute force expansion over all possible configurations. So generally, in statistical mechanics, when you have a partition function of this size, you would expect to have, on the order of hundreds or thousands of configurations, and really here, just a very small fraction of them actually survive and contribute to the results. So it is in that sense, this is really a good combinatorial formula. Okay, so I would like to say a few words about how we prove this, and I think the method is arguably as pretty as the result itself. So we actually have a proof that is entirely in terms of the Yang-Baxter equation, and the message really is that we're trying to consider this expansion here, so expanding McDonald over the Shor basis with some coefficients. And the idea is this should be interpreted as 2 sides of a Yang-Baxter equation. So the left-hand side of this, which is the integral McDonald, that corresponds to the picture that's shown on the left-hand side here. And the sort of combinatorial side, where you sum over pure polynomials, that will correspond to this side here. And this is an honest equality of partition functions, which is just following from the Yang-Baxter equation. So there is an underlying vertex model here, which I'm not specifying, but that vertex model satisfies this particular equation. So I will now say a little bit more about some of the details here. In other words, I look at a given face of these cubes, what is actually going on. So we'll begin by looking at the left-hand side here, which is supposed to be equal to this integral McDonald polynomial. So we've actually known how to write McDonald polynomials in terms of vertex models for a number of years. This dates back to a result that we had with Jan de Geer and Luigi Cantini from 2015. And that formula has gone through a few evolutions over the years and become a little bit simpler. And so I will give one of the simplified versions of it here. So the underlying vertex model is the following. So I will have a vertex whose 4 edges now, well, they correspond to the following possible states. So at the bottom and the top of the vertex, the indexing states are actually binary strings of length n. Whereas on the horizontal edges, the indexing states are integers that take values from 0 up to n. And in terms of the quantum group structure, this corresponds to essentially the SLN or SLN plus 1 solution of the Yang-Baxter equation. With the slight caveat that the representation space of the horizontal line is fundamental representation, but the representation space of the vertical line, we've done fusion, in fact. So this corresponds to actually antisymmetric fusion of the vertical line. So we understand very well where this comes from in terms of the quantum group structure, and one can go ahead and work out very explicit formulas for those weights. And this is just to say that there is a pictorial representation of such vertices in terms of lattice paths, which relates to the pictures that I was drawing previously. So essentially, the values that you prescribe to these horizontal edges, they tell you, in this case, that I have a path of color 1 that enters from the left and a path of color 2 that exits from the right. And the path of color 1, it then makes its way to the top edge here, where the top component of this vector is equal to 1. In this case, this second component is equal to 1. And that's the reason why I have a particle of color 2 that emanates from the bottom. So anyhow, there is some combinatorial way of understanding these weights. And more explicitly, this is what they look like. So I don't want to go too much into the details of what's here. It's just to say that there is a very explicit formula. And notably, all of these weights are just polynomials, maximally of degree 1 in the spectral parameter x. And also, they depend on this t parameter, which is related to the quantum deformation parameter. Okay, so we have some very explicit formulas for those weights. And the idea is that you then take those and you put them into a partition function, which is sketched at the top of the slide. So I don't really have sufficient time to explain all the details, what is happening here. But the basic idea is that you have a collection of n paths that enter through this column here. And they go through the lattice according to the vertex weights that are given on the previous slide. And there is one subtlety here, which is that really you should think of this thing as living on a cylinder. So the paths are essentially allowed to wrap around the cylinder, such as the red one does in the picture here. And every single time that you wrap around, you get a power of Q. So the Q is a kind of winding fugacity of the model. And the claim is that if you go ahead and compute the partition function of this model with these particular boundary conditions, this is actually equal to the integral McDonald polynomial that I defined earlier. So this is a result that we obtained in this paper from 2021 with Amol Agarwal and Alexei Borodin. But as I said, the original result, which was for a slightly different model, dates back to the work that we had with Luigi and Jan from 2015. And one thing that we found out afterwards, which was not obvious at the time, is that actually this vertex model description, there is a very simple bijection between this and the combinatorial formula that was obtained by Hagelin, Heyman, and Löhr. So really, this formula here is completely equivalent to what they found. And it really says that their tableau formula is in some sense a very good one because it relates to integrable models. Okay, so that's the McDonald polynomials. And in order to play this Yang-Baxter cube type argument, you would also like to have a way to encode Schur polynomials using vertex models. And there are many different ways to express Schur polynomials using vertex models. So the one that people are perhaps most familiar with is in terms of non-intersecting lattice paths. But there is a slightly different version, which makes use of the model that I defined a few slides back. So in that model, one has binary strings of length n. So that's the values for these states at the top and the bottom. And in order to get Schur polynomials, one restricts to the case where this n is equal to 1. Okay, so basically, you get down actually to a 6-vertex model in that case. And you consider then a partition function of that 6-vertex model, subject to some boundary conditions that, again, will encode whatever partition you're looking at. And the claim is if you compute that partition function, this gives you the Schur polynomial. And there is one subtlety here, which is actually not that obvious, which is that the model that I defined, it depends on the t parameter. So there is this quantum group parameter in terms of the vertex weights. However, Schur polynomials, they do not have any quantum parameter. So a kind of miracle needs to happen here. And it turns out that all of the t dependence is actually fully explicit in this fully factorized form here as a t van der Monte. So if you compute this partition function, you get the Schur polynomial times a fully explicit t van der Monte. So this is all the ingredients that one needs to basically go ahead and do the computation. And this is essentially what we did. So on the one side of this Yang-Baxter equation, you have these two faces that I'm indicating here and here, which are just frozen. Like here, there's actually no freedom. The paths have their trajectories fully determined. And the only non-trivial piece is this piece at the top, which gives you the integral McDonald polynomial. Then if you use the Yang-Baxter equation, on the right-hand side, you find that this section of the lattice is frozen, and the remaining two sections, they give to you essentially the Schur polynomial and the combinatorial formula for this for these puzzles that we found. So this is basically everything I want to say. I am, of course, suppressing a lot of details. So I do want to stress that these coefficients, we have fully explicit vertex weights for them. And the Yang-Baxter equation that we're actually using here, it seems to be a new solution of the Yang-Baxter equation. And we think it's very nice that this leads to a resolution of this problem purely at the level of vertex models. So I will stop there. Thank you very much for attending and listening.
Michael, so do we have any questions? Anyone online?
Yes, I want to ask.
Vladimir,
It's
yeah.
about the solution of the Yang-Baxter equation. You have the parameter n, small n, yes?
Yes. Yes.
Small n is equal to 2. What would be?
If small n is equal to 2, you're asking what solution this corresponds to, or?
Yeah, what solution of the Yang-Baxter?
Well, I don't know how to connect that to any model that might appear in the literature, but I can tell you very explicitly how we obtain these vertex weights. So we start off from just the fundamental, in this case, in the case of your question, you take the fundamental SL3 solution of Yang-Baxter equation. And what you do is you perform fusion of both the horizontal and the vertical line. But the type of fusion that you perform is mixed. So one will be a symmetric tensor representation, the other will be an antisymmetric tensor representation. So in that sense, the model is not new, but the explicit form that we obtain for the vertex weights is new, because actually computing those weights in explicit form is rather complicated. So hopefully that clarifies.
Yes.
Any other questions? I'll just thank Michael for sharing.
Thank you.